Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. It's a pleasure to be here. It's the first time I visited this lab. So I'm going to give a talk about various kind of stochastic processes that underlie some load balancing algorithms. It's going to be survey-ish in style. And it's mainly a theoretical talk, but I'll try not to go into, I won't go into any proof detail. I'll try to give kind of ideas how the results are proven. And if you want to ask more questions about the proofs themselves, feel free. If you want to ask more questions about actually the applications and how these things are used, then that's fine as well. So the talk will cover something like 6 papers. So I suppose I won't manage to talk about everything. So we'll see how it goes. How much time do I have? Is it 1 hour? All right, that's good. Okay. So what is the basic model? The basic model is we want to place m balls into n bins sequentially, where we can insert them fast. We can look up fast. So think of the balls as if they have names, so we can look them up. And the goal is to have a balanced allocation of the balls across the bins. So the load of the bin is just the number of items that it contains. And our measure, what we measure, the metric that we measure is the gap, the difference between the maximum load and the average load, or the maximum load and the minimum load. It depends on the context. Now, of course, this is just hashing. This is often called hashing. So the way we implemented it, we have the bins. Will typically represent something in an application, but we'll keep it kind of abstract in this talk. And then an item arrived, and typically we use a hash function because we would like to reconstruct the random choices given the item. And in this case, for instance, we just place it, so the function will decide to place it in bin number 6. And throughout this talk, I will ignore the fact that this is actually a function, and I will assume that if I want to sample randomly, I just sample completely uniformly at random. The theory of how to construct these functions so that they are provably correct is probably the topic of another talk. I'll just completely ignore this.
Questions. You skipped over why you just don't use round robin, which would guarantee you very good gaps in everything.
Right, but you won't be able to look up fast.
What do you mean by look up?
So say the bins have names.
Yes.
And then, given a name, you want to locate where it is. So if you use a round robin, it is...
If the bins have names?
If the balls have names, the items have names.
Okay.
So if you want to find them and you place them using a round robin, then you don't have any clue where you've actually put them.
I see, unless you have some lookup table.
Which is exactly what we're... which is exactly what we're constructing. Okay, so basically, this is just hashing, right? All right, so this is self-explanatory. So what I've described here is the first thing that comes to mind is, sure, let's just assume the hash function is random, place each item at a random bin, and I will call it here, thinking about the future slides in mind, the one-choice scheme. So in the one-choice scheme, we just place each ball in a random bin. And this is well understood. The reason it's well understood is because the placement of balls is now independent from one another. So if you think about a specific bin, for instance, just bin number 1, then it receives a ball with probability 1 over n. And this experiment is repeated m times, so this is the binomial distribution. So each bin has a binomial distribution, and the dependencies across bins are very small. They are in our favor anyway. They are negative, and so it's just easy to understand. So this scheme is very well understood. And just to understand the way I draw the plots, because it's a little bit strange, what I kept constant is the average. And now this is, so the average is always, zero represents the average. So this is basically the gap, not the load. The y-axis is the gap. So you see that the minimum bin, since when we throw just, in this plot we throw just n balls into n bins, the number of balls is equal to the number of bins, then there are always empty bins. So the minimum is always, the minimum load is always 0, so the gap just grows linearly from 0 to 100 when we throw 100 balls in. And this indicates the average maximum load.
On the negative y-axis, you're plotting the proportional. So the -1 on the negative on the y-axis actually represents positive 100 for the number, total number of bins.
So I'm sorry. All right, I'll do it again. The horizontal axis is the number of balls thrown.
Yes.
And this is the gap. So if you think about this point, then the average is 1, but we have empty bins. That's all right. The minimum load is 0, so we have a gap of -1 between the minimum and the average.
Okay.
And the maximum would be somewhere between 4 and 5, so the gap is between 3 and 4.
There is also a probability, right?
I'm sorry?
The maximum is 4 and 5, the maximum is 100.
The maximum with high probability. If you throw balls into bins using just random function.
Yeah. I could get 100 in one bin. It's not very likely.
Right. So this
The
is
maximum is 3.
so this is the maximum with very high probability. All right. We're in a stochastic.
You've chosen some threshold.
Yes, but it is the right threshold to choose, and and the reason is that from this threshold onward, the probability decays exponentially with the threshold. So in your lifetime, if you repeat this experiment again and again and again, in the lifetime of this world, you will not see a load which is larger than some not large constant times log n over log n. All right, when you throw, if you throw just an unbiased coin 100 times, then you will see 50 plus minus something, but you will not see 100.
So how many standard deviations out are you going?
What you're really saying is if you go beyond that point, your hash function's broken, rather than is more likely to be the case than that you were unlucky with.
Right. Beyond this point, the probability of seeing something larger than this decays extremely fast, and basically reaches a point where it will not ever happen. So I'm a little bit free sometimes in the context of this presentation. I sometimes present events that happen with overwhelming probability as if they're happening with certainty. It's just easier to think about it. And so the way to think about it, if you throw n balls into n bins uniformly at random, you will see the maximum being something like log n over log n. Will be bounded by some small constant times log n over log n. This will happen just with overwhelming probability.
Is it bounded below as well?
Yes, so it's not hard to show that that this is the right number. So this thing, it's nothing magical. If you want to prove it, you just have to write down the expression for binomial distribution, and it's just a straightforward calculation. Now, something slightly different happens if we allow the number of balls per bin to vary. So here I have plotted the number of bins is constant. I don't remember what it is, either 100 or 1,000. And this is the number of balls per bin. And I'm sorry, this is the number of balls, not the balls per bin. And this is the gap, again. So now if we want to think about it asymptotically, then what we'll have is if we throw m balls into n bins, where m is much larger than n times log n, then what will happen is the average would be m over n. That's the average. And the maximum would be m over n plus this expression. this is the this would be the gap from above and from below. And if you want to decipher it, then again we have the binomial distribution in each bin. The standard deviation of the binomial distribution is the square root of m over n, the square root of the average. And we want high probability across all bins, so this is why we have log n here. So again, this is the right number in the terms that the probability that you'll have more than this decays very, very fast.
So these axes here are the same as on the previous plot?
Yes.
You just zoomed out. So if I zoomed into this one, I'd see the same graph as before.
Here.
Yeah,
just
right
this
near,
part.
Right near the origin.
Yes, exactly.
It would look identical to before. You just moved out, moved the scale out.
Yes.
Okay.
But something asymptotically different happens when you move the scale out, right? You don't have the log n over log n. You have basically a dependence on the number of balls here. So the thing to observe is that if the system becomes more and more loaded, we throw more and more balls into these n bins, then the additive gap between the maximum and the average increases in time as well. Yeah.
So the vertical axis is in absolute balls?
No, it's gap.
Okay. But so the gap is the difference in average number of, between the average and the maximum number of balls.
I'm sorry, come again?
The gap is the difference between the maximum
Right, and the average.
number of balls.
Right, right.
So
the thing, the way to think about it, if you have something like 10,000 balls per bin in the system, so think of an application where you have, I don't know, some storage system of small blocks, and 10,000 seems like a reasonable number in this domain. Then you will have a gap of a few hundred, typically. So you may have 10,000 plus a few hundred in the maximum, which in many applications is acceptable. But if you want to provision for the maximum, then you may want to check whether you can reduce that maximum with little effort, which you can. Okay?
yeah, it seems that in practice the difference will be quite small, right? I mean, the thing you are trying to improve is already very good.
Right. The thing that I'm trying to improve is already very good. That is correct. But it depends on the application. So in many applications, there is no need to try to improve it. There are applications where provision is very expensive and you provision for the maximum. For instance, if you want to implement certain types of hash tables and you don't want to have any dynamic allocation of memory, then the size of each bin basically has to be the maximum. So if you reduce the maximum by a little bit, you multiply it by the number of bins in the amount of memory that you throw into the system.
Okay, so focus there. I finally got a handle of what you mean by maximum. You mean something you said before, it's the point beyond which the probability decays exponentially. That's good. But you're also implying that it's a point that you might meet in practice.
Right.
If it was already vanishingly, in your lifetime unlikely to happen, you wouldn't be worrying about this provisioning question.
Right. So these.
Is it 1% or 0.1%?
So you're asking about the phenomenon that is very common in stochastic processes. That sometimes I don't even mention it explicitly, and I probably should have. So what happens with these types of processes is that their behavior is very well concentrated around some point. And the idea is to find out this point. So there is some point where you are extremely likely to be close to it, both from above and from below. So it's kind of the right answer. And for the sake of a presentation, you can just give the number as if, this is what you'll see.
I just want a number. So if I run your thing and I say, is it 1% unlikely? One time in every...
No, much less than 1%.
Much less. One time in every 1,000 I'll need my maximum provision.
Well, it depends on what constant you have here, but your probability will depend exponentially on the constant, and exponentially on the expectation. So you can, if you vary, say, the number here between 2 and 10, then you will get 2 to the, like 1 in a million or even more.
Okay. Okay, that kind of stuff.
Yeah. All right, so can we do better than this? I mean, can we improve? And the main protagonist of this talk now appears. So here is a different scheme, which is algorithmically at least very similar to the previous one. And all we say is the following: we place the item in the lesser loaded of 2 random bins. So we now sample 2 bins, and we just place it sequentially in the lesser loaded of the 2. So now we have dependencies not just across bins, but between the placement of the balls themselves. So it's much, much harder to analyze. I hope to give some idea of how this analysis works. But now for the m equal n case, for the lightly loaded case, where we throw n balls into n bins, we have reduced from log n to log n. So, I don't know, politicians would call it an exponential improvement.
Meaning barely measurable.
Yeah, well, between log n and log n, I suppose technically it is a kind of Clintonian kind of truth. So how does one come about proving this, this result? So this would be a very high-level proof, but it's kind of subtle. It's not mine. It's, as I said, Azar et al. From 94. And it's a proof by induction. And one perhaps has to think about it a little bit to see kind of the ingenuity of this proof, because it's a very strange type of induction. So let's see what we induct on, and it's not the number of balls and it's not the number of bins. That's kind of the clever part. So we need to define a variable beta I, which is the fraction of bins with load at least I at the end of the process. So the induction would be kind of on our bound. We will assume that we have some bound on beta I, and then we will try to deduce a bound on beta I plus 1. So bear with me here. So the base case, beta 3 is smaller than a third. We throw n balls into n bins. We can have at most a third of the bins with more than 3 balls, right? Because we have just n balls to begin with. So this is true with probability 1. This is just a counting argument. All right? Now, let's say we know beta I. So we know we have a bound. We condition on beta I. We have a bound as to the fraction of bins with at least I balls in them. What do we know about beta I plus 1? Well, in order for a bin to have I plus 1 balls, there should be a ball that when it was placed, it was kind of placed in height I plus 1. So both of its random choices had to come from bins that were of height I. But there are just a beta I fraction of them. So the probability that this happened is at most beta I squared, because this is the fraction at the end of the process. So beta I squared is an upper bound on the probability that a ball falls in height I plus 1. And then we have only n balls. So we get kind of this equation.
Okay, so the less than comes because beta I is only appreciable at the end.
Right. Before then it's even lower, so that's why we have an inequality here. And now ignore the fact that this is, so let's assume that this indeed happens, because it happens with high probability and so on. This is kind of where it gets a little bit dirty, but let's assume that this happens. So what is the kind of recursive progression? For beta 3 is a third, and each time we step from beta I to beta I plus 1, we square it, right? If we drop the n's, then we get that beta I plus 1 is at most beta I squared. And if we get something lower than 1 over n, it means there aren't any more bins, because we have just n bins to begin with. So how many times do we need to square a fraction until we get 1 over n? Well, exactly log n times. So it's kind of a clever proof. And this is the idea, and now kind of there are some technical details to show that it works, but this is basically all there is to it. And you can see from this proof that if you had 3 choices instead of 2 choices, then it wouldn't really make a big of a difference. It would change the constant before the log n slightly. So the truth is that it's the exact expression that you get is log n divided by log the number of choices. So yeah, we'll just stick to 2 for this point.
Didn't happen when we go from 1 to 2.
Yes, exactly. The dramatic difference is between 1 and 2. Between 2 and 3, it's a very mild difference. Yeah, so this is very interesting.
Sorry, but if the number of choices is not constant, like instead of 2 bins, you have like I don't know, log n bins to choose from, then you will see this.
Right. That's true.
Log n bins. That's 4, right?
So according to the scheme, you would need log n bins in order to have it a constant load.
Yeah.
But you can get it down to log n with a slight modification that I won't talk about in this talk. So just observe that this proof really relies heavily on the fact that the number of balls is equal to the number of bins. We've used it in a couple of places, and it completely breaks down if we vary the number of balls. If we want to think of this scheme for so this kind of solves the hash table case where the number of items is very similar to the number of slots, but this doesn't solve the, say, distributed storage case where we may have arbitrary high load in each of the bins. So this was solved 6 years later in a remarkable paper by Bernbrink, Zumay, Steger, and Woking. And this is a much harder proof that I won't talk about here. But the remarkable thing is that the gap stays log n even when m is arbitrarily large. So now the gap is independent of the load of the system. So if we plot it, so now this is the 1 choice and this is the 2 choice. So it just stays flat as the load of the system increases, which is again a very remarkable phenomenon. And I should mention that the log n is, in practice, is the constant here is like 1. So in practice, you will never see a gap of more than 4 items, additive gap of more than 4 items for 1,000 bins. So to your question with this, if you can afford to do this, then you have reduced the gap between maximum and average from a few hundreds to 4. So if it's worthwhile, then it's worthwhile. If not, then it's not. But it's a kind of dramatic improvement over something that was pretty good to begin with.
For all practical purposes, log n is in fact constant, right? So even if n is the number of protons in the universe,
log n is small, yes.
log n is kind of
Right.
6 or something.
Right.
Really small.
Right.
And constant.
Right.
So adding more bins.
Right. Adding more bins doesn't matter. That's true. So this basically shows that this very simple algorithm keeps. I mean, it's almost hard to believe. I had to kind of simulate it a few times to believe it myself. But you have 1,000 or 10,000 bins, and you just let the computer run for a day and throw a few billion balls into these bins, and then the gap is 4. It just keeps the allocation completely balanced. So if it's important and you can afford to do that, then it's worthwhile. So I won't give the proof. I'll say that the really hard part of the proof is getting the number log n, and this is actually a computer-generated proof, and it's very hard to verify. But why the imbalance is independent of m is actually much easier to show, and I'll just show the idea here. So let's say we have just 2 bins. So think of the gap as if we have just 2 bins. So we have x1, it's the load of bin 1, and we have x2, it's the load of bin 2. And think of the gap as x1 minus x2. So it could be negative or positive, but this is the difference between the 2 bins. So now I'm looking at maximum minus minimum. And if we use the 1 choice, then with probability half we put a ball in bin 1, with probability half we put the ball in bin 2. So the gap either moves to the right or moves to the left, right? It depends where we put the ball, if we put it in the larger bin or in the smaller bin. So basically, if we have just two bins, the gap behaves like an unbiased random walk on the line. And we know that after time m, we will be in distance root m from the origin. That's the same root, average root m over n that we've seen previously. However, in the two-choice case, with probability half, if you think about it, we're basically biased towards the zero, because how can we increase the gap? Only if both of our choices were for the largest bin. So say x1 is greater than x2. In order to increase the gap, we need to place the ball in x1, and we can do that only if both our choices were bin 1, which happens with probability 1 over 4. So with probability 1/4, we will increase the gap. With probability 3/4, we will decrease it. So basically, we have a random walk that is biased towards 0. So it always moves again towards the balanced, towards the point 0. And it is well known, and there are many ways to show it. I won't show it here in the Markov chain theory, that this Markov chain, this walk, the expected distance from 0 is constant. It doesn't matter how far we look into the future.
Even better by choosing the second bin to be different than the first choice.
Well, it will help in the case of two bins, because then you'll get around robin, right? In n,
probability 1, it'll be
right, but in n bins, it will not make a lot of a difference. So just as an illustration now,
okay.
Right? And if you just want to understand why the distance is constant, then if you think of the stationary distribution of this walk, then it's not really a distribution. It's a stationary measure that has the same measure, the same weight for each node. Well, this Markov chain has a stationary distribution with an exponential decay, so it has a stationary distribution with a finite expectation. So this is one way, for instance, to prove this result. So this is the intuition why the balance is independent of m. Why it's actually log n, why it's so small, is a very hard result. I will not show it here. Okay, so there was a research application, a research kind of a system that we built a few years ago, a distributed storage system that was based on these ideas. So we had racks, and these rectangles represent the servers, and we kind of used consistent hashing to place items into servers. So each item got an ID, and if the ID fell here, then it was placed in this server, as you do in consistent hashing. And in storage systems, we want to replicate the items, and we want to replicate them across racks. So what we did is, if you want, say, three replicas, then we chose 4 racks. So we had 4 potential servers, and we just put it in the 3 less loaded of the 4. And we indeed got a very, very well balanced across machines distributed storage system. So this worked very well, even though what happens is the following. The multiple choice is not always used. So the front end that places the system, sometimes, some request timed out, and it found itself basically contacting only 3 racks, only 3 servers, and placing the item in those 3, and basically not using the extra choice in practice. This happens. The servers are heterogeneous. The data items are of different sizes. And so on and so forth. So from a theory point of view, we want to generalize the model a little bit. And so far, I haven't talked about my own results. From now on, basically, in the past few years, I occasionally managed to show how much the two-choice paradigm is basically robust and why it works in practice. Because the clean model that I have shown is rarely really implemented as shown. Right? We have all these things. And sometimes they can really ruin the scheme. So it's important to understand when does it work and when it doesn't. So let's see what happens if occasionally we just don't perform the two-choice paradigm. And this result is the result that I'll be a little bit more technical. The other results I will really just state. Yeah.
Just have a quick question. The story example you actually had, so is it generally those results broadly hold true if you take sort of k plus 1 things and
Yes.
k?
Yes.
Okay.
So this I won't even show. This is straightforward to show. Yes. Yeah.
I just didn't get one thing in the application that said, basically if, like you say, you use round robin and non-basic round robin. So the first being in the first chain, the second rolled in the second, etc. Well, you have, you know exactly which bin you put, and it's completely balanced. I don't see why you have to choose it.
Well, in a storage system now, if you have a request for an item, how do you know where you put it? It depends on where it was in the stream of items placed, right? Exactly.
But with two choice, how do you find it?
Yeah.
You haven't told us about.
All right. So the cost. So this is the cost. So with two choices, you know that it lies in exactly one of two known choices.
Yes.
So you have to check both. All right. So this is the cost of two choice. You have to contact two servers when you place it, and you have to contact both of them when you search for it. But it could be only in one of those two locations. If it's not there, it's not there. True. So this again motivates the doing the two choice sometimes. So we call it the 1 plus beta choice. And what we do is the model is as follows. When we see a ball, then we with probability 1 minus beta, we basically do the one choice scheme, and with probability beta, we do the two choice scheme. So just occasionally, we don't do the two choice scheme. So it has two advantages. The expected number of bin accesses is less than 2, so it reduces the cost of, or the expected cost somewhat, because occasionally you do need to access just once. And it can model the case where, for instance, you don't have time, or the reported load is sometimes just not up to date, so you make the wrong decision occasionally, which also, of course, happens in practice. So when you make the wrong decision, you can think of it as if you basically did the one choice.
I don't understand that second bit. I mean, typically, by the time you access the object, you're not going to know that that was one of the objects you didn't pick two choices for, so you'd look at both places anyway, wouldn't you?
This random decision, whether you do 2 or 1, can also depend on the identifier of the item, right? It could be a hash function of the item. And now then you can, given an item identifier, you can compute whether...
only if you're really lucky, not if you have
right.
maps and stuff.
Right, that's true, that's true, that's true. Yes, that is true. All right, so how do we approach this thing? So if you think about the intuition that we had of the random walk, of the biased random walk towards 0, then this is still true. We will still have bias towards 0 and a distance of 1 over beta after m steps. So the question is, can we generalize this intuition for a larger number of bins? The vector of loads now would be n-dimensional. We can't model it by a simple random walk. And the kind of intuition, the high-level intuition that kind of breaks down when the number of bins is large. So it's easy to see that if we throw a small number of items into the bins, then basically the beta fraction, or the 1 minus beta fraction of the items that were thrown using the one choice cause the load to be log n over log n here. So it's not very helpful. I mean, the fact that there is a small fraction of the items that we try to do something more clever is not really helpful. But when we throw more items, we suspect that actually they will be extremely useful. We just don't know exactly how much. And this is the goal of this work. So let's simulate it. And what we see is, in fact, that if these two inner lines are the two-choice scheme, then this is the 1.5 choice scheme. So we see that we lose very little in practice by basically giving up on half of the items. And And this is, I think, quite remarkable. Remember that the half of the items that use the one scheme on their own, they have kind of a scaled down graph like this. And the other half is actually used to balance it out, and it works remarkably well. So, I mean, you can convince yourself that it's a surprising result if you want to. So we basically completely analyze this case in this work, and I'll show you a high idea of how it's done. So we use what is called a potential function. So let xi be the gap of the ith loaded bin. So we sort the bins according to their gap. And xi is the gap of the ith bin. And now we define a potential function phi, right? After many years I still can't remember the Greek letters. So phi of t is just the sum of some exponential of these gaps. So this is a potential function. What you need to observe is that this potential function becomes very large if we have a bin with high gap. If we have a heavily loaded bin, then this xi is, x1, say, is very large, and then this whole expression becomes very, very large. And if the allocation is completely balanced, then all the xi's are 0. So this is e to the 0, and this is 1, so we basically have n. So if phi is n, we are completely balanced. If phi is bounded by some polynomial of n, it means that the most loaded bin, x1, is at most log n. So we hope to show this. We hope to show that phi is bounded by some polynomial in n. Right, so clearly if we have an allocation that is completely balanced, then phi is expected to grow, right? Because we can't keep it completely balanced all the time. So what we hope to show is that we have some, if we look at the kind of how phi behaves over time, we hope to show that there is some point below which it has some arbitrary behavior, but above which it is biased towards 0. And then to use it to show that actually the expectation of phi is bounded. And indeed, this is enough. If we can show that phi has a bias towards 0 from some point that is polynomial in n, then we're done. It will work.
The hope is not to show that it's log n.
No, it is not log n. I mean, that's not the truth.
But what we saw in the simulation, it was log n.
You know, in the simulation, you actually saw log n. It's not hard to show a lower bound of log n, but it's trivial to show a lower bound of log n over log n. Because if you just throw n items, then the expectation is 1. The half that were thrown using the one choice is log n over log n. And you can show it's a subtle probabilistic argument, but it's very believable, that you cannot reduce the gap. You can hope not to increase it, but you cannot expect, the gap to reduce over time. So this is what we want to show. And indeed, we managed to show it. So basically, you just open up, write the equations, and this is what you get. You get that there is a bias towards 0 if under two conditions. One is we need that the probability that the ball falls in the light bin, in the, say, n over 4 light bins, is slightly greater than 1/4. Which is true whenever we have any scheme that has a bias towards the light bins, which is what the kind of 1 plus beta choice has, right? You are more likely to put a ball in a light bin than in a heavy bin. That's the point. So if we have some bias, then it works. So far, this is great. This is exactly our scheme. Our allocation rule favors light bins. But there is another kind of technical problem with this function. We want the lightest bins, want the n over 4 lightest bins to actually be light, to be below average. Or in other words, we have a problem if the allocation is like this. If almost all the bins are basically above average, they have a positive gap, and we have one last bin that was terribly left behind. In this case, in fact, this potential function does not work. It's not hard to show. And intuitively, it's easy to believe it because our potential function, we said that it is very sensitive to the load of the heaviest bin, right, because it's exponential. But it is very insensitive to the load of the lightest bin because then we have e to the minus beta xi, which is a very small number. So, I mean, the potential function is basically identical if all the bins were above average and if we remove this bin altogether, right? So clearly it cannot, show that that the allocation is biased, is balanced for this type of allocation. So how do we fix it? Well, we can think of another potential function. Now, if we do the same potential function with a minus beta here, then intuitively everything is reversed. In practice, it's not. You have to reprove everything. But intuitively, everything is reversed. Now, this potential function is very sensitive to the bins that fall behind, but is insensitive to the bins that are ahead, that are too loaded. And therefore, if we just add them up, then this turns out to be good. Now, if the allocation is more or less symmetrical, so kind of half of the bins fall behind, half of the bins are ahead, then both of these functions are good. And the trick is to show that if the allocation is really far from being balanced, then one of those potential functions increases and one decreases, but the one that decreases dominates the one that increases. So all in all, this is a good potential function. So the theorem we can show is that this potential function, this gamma, the potential function that we came up with, on expectation is actually even linear, or this has n over beta. Now the gap is just x1 minus xn. So this basically shows that the expectation of the gap is small, is logarithmic, which is what the simulations show as well. And we do have this result that this would be highly concentrated around this. It's we just can imply Markov's inequality, and Markov will work because the potential function is exponential. So basically, Markov's inequality provides the exponential concentration that we typically have in these types of processes. And it is tight even for two choices. And the reason that it is tight, I mean, I've just said that in two choices the gap is log n. But log n is the gap of maximum minus average. In the two-choice case, the minimum actually lags log n behind. So we do have a log n between maximum and minimum. And this is what this technique can show, that the gap remains log n between maximum and minimum, even if we do the 1 plus beta choice instead of the two-choice. In the two-choice case, there is something else that happens, and that is the maximum is much closer to the average than the minimum. And this requires the very subtle arguments that they used computers to show, and we cannot show in this case.
So in your graph,
yes,
you had the one you had several slides ago. You showed the sort of the quadratic on its side, like the picture for the two-choice, and then you had pretty much constant for one choice. Then you had that flat ones for two-choice and for 1.5.
right.
So 1.6, 1.7, 1.8, 1.9, they must sort of move out to join.
No, they actually go closer to these two.
I went the wrong way. So 1.14, 1.3.
Yeah, they slowly.
So they can't stay constant.
No. They just lift up a little bit.
Okay.
So what point?
So when we get to 1.
All right. So in order to get to 1, you need to be close to 1 in an amount that is dependent on the number of bins. So you have to be like 1 plus 1 over root n. Then you lose it. So you can fix it by increasing the number of bins. You can always, if you keep the number of choices constant, you can always fix it by increasing the number of bins, so to speak.
So the other way to think about it is you should use two choices, so at least 1 over root n of your...
Yes.
Okay.
Yes. Exactly.
That's the bit I need to write
Yeah,
down.
I understood that.
All right. And what you can see here is that the maximum is closer to the average than the minimum. So, I mean, this diagram is not aimed at showing that, but this is log n, while this is log n, also in the two choice. All right, all right. I have 10-15 minutes left, so I'll just be very light on technical results. Just show, basically state some other results, or mainly state them with some intuition. So what happens if items have different sizes? So now what is the model? So clearly, if the size of items is decided adversarially, then there is nothing we can do, because an adversary can always have the last item be very, very large, and there would be no place to place it without causing imbalance. So in the stochastic domain, let's assume that the sizes of items are drawn independently from some distribution that just assigns them the size. So it's a reasonable thing to do, say, in storage systems. If we want to place files, then files come from some distribution. And our assumption here is that whenever we see a file to place, its size is independent of the files that were before it and after it. It's just drawn independently from some distribution. So now the model is as follows. An item arrives, and it is assigned a weight from this weight distribution W. And then it is placed using whatever scheme we want. Okay, so is the model clear? It is a very, I think, a realistic model. I think that's the main problem with the applicability of the original two-choice scheme in many scenarios. So this is actually a very tricky problem. So let's work through some toy examples just to convince you, kind of toy examples that it's easy to see what goes on, to convince you that the theorem is very hard to formulate. So let's assume first that the number of items is equal to the number of bins. So this is our domain. And let's think of the simplest weight function. It's just uniform in 1 and 2. It either assigns a weight of 1 or a weight of 2. Okay? So in this case, there is no real reason to even consider the weights of items, because if we just ignore the weights, then we have log n items per bin. And on maximum, we will have then 2 log n, a weight of 2 log n. In practice, it would be 1.5 log n, because they're independent of our choices. So, I mean, in this case, just ignore the weights and you're still doing okay, which makes sense because the weight is meaningless, right? It's either 1 or 2. So what happens if it's a just slightly more interesting distribution? Say it's the geometric distribution. Now, if we have with expectation 1, so when we have n items, then the total weight would be n, basically, very well concentrated around n. So the average is still 1. However, with high probability, there will be one item that is very heavy, say roughly half log n. So we know that the gap would be at least half log n just because of that particular item. And if we ignore weights, in fact, we can even use the one-choice scheme. We don't need to use the two-choice scheme. We will have at most log n items per bin in high probability. And the total weight of log n items is again bounded by some other constant by log n with high probability. So basically, what we have is that we will have a gap of log n no matter what we do. We can have some control over the constants, but it's not very interesting. So the conclusion is that the case where m equals n is just not interesting. Either we can ignore weights, or weights basically dominate everything that happens.
Not interesting as in insoluble.
Not interesting as it's very easy to understand what's going on. If the weights are very extremely well concentrated, then we can ignore them. If the weights are just slightly more interesting, then they dominate what's going on. So in terms of the math, it's not interesting. All right?
That's right.
No, in terms of the math and application, means that it's good for another theorem, right? So it's, I mean, the whole terminology shifts a little bit. So let's think of the heavily loaded case. So say m is arbitrary, so the number of balls is arbitrary, and the weight function is again uniform in 1 and 2. Now if we just look at the average, so say we ignore weights, and we just look, and we have a perfect allocation scheme, so we put m over n items per bin, then just the weight, so the expectation is 3 over 2 m over n, right, because that's the expected weight of a ball, and just w would cause the maximum to be plus minus root m over n. So we lose the exact term that we lose in the one-choice scheme already from the weight, already from this kind of very stupid weight function. So in the heavily loaded case, it is clear that we have to take weights into account, even when we have the easiest weight function we can think of. Okay? And it's not trivial to see that, so even our argument that, you know, we have a bias towards 0 is not straightforward, and it's really kind of a little bit mysterious what goes on. We can imply the intuition of a biased random walk, so not straightforward, but we can use it, so we can kind of assume that the two-choice would remove this and would put some constant that is independent of the number of balls here, but it's not easy, and we'll see what goes on. All right? So the first thing to observe, so this is a previous work, but the first thing to observe is think about the 1 plus beta choice. In the 1 plus beta choice, the crux of the argument was these potential functions that were exponential, e to the gap. Now, if the weight distribution W is such that if we exponentiate the weight, we still have the expectation constant, things behave well, then in fact we can do the entire proof that we did for the 1 plus beta choice with weights. Nothing terrible actually happens. Yeah?
Getting a bit lost. When you say take weight into account, you mean in the proof or in the actual choice?
In the actual choice, of course, and now in the proof as well. We want to, I mean, we put it in the algorithm, and now we want to prove its performance. So I do it in the choice, and then where does it hurt the proof? So what I claim is in the proof we take the weights of bins and we exponentiate them, right? We take e to the gap, and then we throw it into the potential function. And the nice thing, the technical thing to observe is that if the weight function is well concentrated so that exponentiating it doesn't kind of cause it to go crazy, the expectation to move to infinity, then in fact the same proof holds. So, and we get this bound. So this is I think pretty amazing. So if you have the following thing, you have items coming from an exponential distribution that has this thing, and I'm asking you what would be the weight after I throw m balls. So there will be an item of size log m. There would be a very large items, right? The size of the items basically depends on m. There would be an item of size log m, but the gap would still be log n with high probability because the balls would actually compensate for it. Okay?
Sorry, I'm just still stuck. When you're using the weight in the algorithm, that's just you're using the weight to calculate load, but you don't actually care about the weight of the individual item you're going to chuck into the thing.
Right,
Okay.
right. So basically the algorithm is the same. You sample two bins, you check their total weight, and then you put the item into the slot of the two. Yeah.
The distribution is heavy then.
That's the next slide. It's a good question. So this is basically we understand fully what happens with the very, very thin-tailed distributions. Distributions that, so basically distributions where if we exponentiate them, we still have a constant expectation. Nothing bad happens. I mean, you can use even the 1.5 choice and it still behaves very well. which is what we see in practice. So this is a good match between theory and practice. So in other weight distributions, we couldn't show exact bounds. It became very, very hard. But we show what we thought at the time was quite surprising. Basically, all we need from the weight distribution is to have a finite variance. And we need some minor technical details about it that I won't describe. But basically what we need is that the variance would be finite. So even for heavy tail distributions, if their variance is finite, and most heavy tails distributions have a finite variance, then what we can show is that the gap is independent of the number of items that we throw. We can't show a very good, we show some polynomial in n, which is clearly not tight, but it's still independent of the number of items, which is kind of surprising because if you have a log normal distribution, then you will see arbitrarily large items as time goes by. Huge, humongous items, but still at any given time point in advance, what you expect to see is a more or less balanced allocation. So in the remaining 5 minutes, let's discuss what happens when the bins are not identical. So first, what I want to argue is that the way to model non-identical bins is to claim that the sampling distribution is not uniform. And I'll justify it in a second. So we make two choices, right? And we so far assume that each bin is sampled with probability exactly 1 over n. Now what I assume is that each bin is sampled with probability pi. Bin I is sampled with probability pi. And I have some bound on how biased this sampling distribution is. It is between 1 over alpha n and beta over n, where alpha and beta are greater than 1. Now why is this a good way to model heterogeneous bins? So I'll give two examples. One is, say we want to use it for consistent hashing. So this is the hash space domain, and these are the bins. And now in consistent hashing, if a new item arrives and is placed here, then in effect what happens is that the probability that we sample this bin and this bin is half of the probability that we sample the other bins. So in dynamic systems where bins arrive and bins leave, then it is likely to assume that inherently we have a bias in the sampling probability. It's very hard to avoid it. So this is one type of heterogeneity. The other type is, of course, if this bin is much larger than the others. So say bin 2 is 3 times the size of the other bins. So clearly what we would like is to sample it 3 times more often. But this often means that we need to adjust the sampling procedure to the size of the bins, and we don't want to do that. So the way I want to think of it is that this bin basically simulates 3 bins, and now these 3 bins, they share the probability of bin 2. So each one of these bins is sampled with probability 1/3 than the other bins. And if we have a scheme that is robust to that, then we can afford to have some heterogeneous bins without actually adjusting the sampling procedure itself, which is, I think, a desirable goal. Now, the first thing to observe.
Can I just ask you to clarify that? You're basically saying you're going to treat a large bin as if it was an integer number of regular size bins.
Right.
So you're considering only heterogeneity by an integer line.
Right.
I just want to be clear, I know it's not criticism, but I just want to understand that that's what you're saying. So
Right, but it doesn't. It could be non-integer. It doesn't really matter.
It's basically the increase, right?
Yeah.
One bin is like
Yeah.
So you basically extend this from 1 to 7 to say to 1 to 9, where bins 8 and 9 also get chucked in bin 2.
Right. So what I want to say is that if we have a scheme, if we can show that the, say, two-choice scheme, it will not. But let's say that the two-choice scheme can handle a case where P1, P2, and P3 are 1 over 3n instead of 1 over n. Whereas we have bins that are sampled with a much smaller probability than 1 over n. then in fact this scheme would also be robust to the case where some items are much larger than other items, because then we could think of these large items as if they are composed of smaller items. And then they will get 3 times more items without actually changing the placement procedure. So what I want to argue is that the right model to think about heterogeneous bins is the model in which the sampling distribution is biased. And if we can solve this case, then in fact we capture the case in the previous slide and also the case where the sizes of bins change a little bit, and we will be able to adjust the load of the bin to its size without changing the allocation procedure. So the second thing I want you to notice is that the two-choice paradigm cannot work as is. I think I removed the slide that shows it, but what happens is as follows. So say we have a bin that is sampled with a higher probability. It may be the case that just on expectation it gets too many balls, more than 1 over n balls. So if bin 7 is the highest, is the heaviest loaded bin, and it is sampled with probability P7, then it will receive a ball with probability P7 squared, right? If we sample it twice, it will receive a ball. If P7 squared is larger than 1 over n, we're done, right? It will just get a ball with probability greater than 1 over n, and it will receive the majority of the balls, whatever we do. So is that clear? So the way to solve it is to increase the number of choices. So remember, we have alpha and beta that kind of bound how bad the sampling distribution is. And the main result is as follows. We have some strange function of alpha and beta, but explicit, it's this function, such that if the number of choices is smaller than this number, then it may be the case that we're in a really bad situation. It may be the case, it's not always the case, but it may be the case that just some bins are left behind or not sampled often enough, and whatever we do, they're just left behind. And some bins are just sampled too often that even though we have D choices, it would not overcome the fact that some bins are just sampled too often. On the other hand, if we are even slightly better, if we have more choices, then we're already completely in the two-choice domain, and we enjoy the entire benefit of the two-choice scheme. And I mean, this is a simulation where the probability of sampling a bin is between 1 over 3n and 5 over n. And they are distributed in the kind of worst possible way. And you can see a huge difference between 5 choices and 6 choices. So, I mean, that's something to notice. Yes?
So, I guess I'm just not getting the intuition. Is this the same thing, or why shouldn't we just do that virtual server trick and then use the exact same technique, exact same analysis, just with a larger n, but you've got log n anyway?
Right. So
is that what's going on, really?
So what this means, what you suggest, is that basically the sampling procedure, the hash function, should be updated whenever we say change the capacity of the bins. Right? N changes whenever we...
Oh, I was thinking n doesn't change, but it's just very large from the beginning. Much larger than your...
So say you have a completely uniform system. All machines are the same.
Right.
And now you take a machine and replace it with a machine that is twice as strong. And you want it now to receive twice the number of balls. Twice the number of items, because it is twice as big. So how do you do that? So what I'm saying is that if the number of choices is large enough, if you don't use the two-choice scheme, but you use the six-choice scheme, then when you measure the load, you don't just measure the load absolutely, you measure it compared to the size of the item, and you will be okay, as long as they are not wildly balanced, because the 6 choices will kind of overcome the imbalances across the bins in a completely oblivious manner to your actual bin. So you can change, you can replace the bins with one another, and you don't need to touch the allocation rule at all. That's basically what I argue. Okay? Is that more clear?
Yeah, it's just a bit worrying because that 6 doesn't come for free, right? You have to ask 6 servers.
Sure. But nothing comes for free. I mean, changing the front end, changing the allocation rule.
Sure.
But anyway, this is a kind of a math read. I mean, it's. I think these are kind of intuition builders more. It's not. I don't describe working systems. But okay. So, what is the conclusion? I think that a small load balancing effort can take you a long way. I think that's the main conclusion. That basically this model is very robust, and it serves as it explains why load balancing works in practice, because basically everything you can think of can almost provably work. But it also encourages kind of the general heuristic of, if you can afford it, instead of just doing a random decision, try to optimize over a small set of random choices. And this is true in many applications, not just in load balancing. It turns out to be a strong kind of approach for building heuristics. And yes?
Did you try a hash table implementation and just see if that is...
Oh, there are a zillion papers of hash table implementations. And
you're using this heuristic to improve it?
Yes.
So
And in fact...
measurable benefits? I mean, is this a kind of... If you're building a hash table, of course you should do this?
Well, you shouldn't do this per se. There is a slight tweak to the scheme called the go left scheme or d-left hashing, which even improves the load more. I'd be happy to talk about it after the talk. And there are improved benefits. So in scenarios, in architectures where D choices come for free, more or less, because you can check in parallel, and yet memory is very expensive, then this is the scheme of choice. So basically it's hardware. It's implemented in routers and in hardware. It's a very good hash table to implement in hardware. And I'm not sure, I would expect that handheld devices use it as well, but I don't know that for a fact.
I know it's a digression, but this is really interesting. So what you're saying is, if I know how big my cache is, you can tell me how associated it should be. Am I interpreting that correctly?
Not sure.
Okay, we'll talk back later. That would be very cool.
And all right, I know I'm over time, but I really want to just finish with a very strange open problem. So this is the absolute last slide. Sorry for the disappointment that there is a slide after the conclusion slide. But so a very natural scheme that there is just a system in our lab that does this. I mean, and this is a very, very natural, storage scheme. You want to place an item in the scheme, then you sample a bin, and then you put it either in bin I or in bin I+1. And this has very desirable properties because it basically means that server I can back up server I-1 to some extent, and it's very local. But somehow this is very mysterious. So the dependencies in this system, I'm thinking about it for more than a year. And I can show a gap of n log n. It is a nice result. It is not trivial at all. But simulations strongly suggest that the right number is root n, and I really don't know how to do it. So
what do you mean by either in I or I+1?
So you just sample. So you arrange. Imagine your servers are just connected in a cycle, and you just put it in a bin or the bin next to it.
Yeah, but what determines the date of choice?
I'm sorry.
Is it random or?
So you choose first. You initially choose a random bin.
Yes.
This kind of guarantees that the whole system is more or less balanced, and then you put it either in that bin or in the bin next to it.
Randomly.
Sorry?
The lower loaded of the two, right?
Yeah, the lower loaded of the two.
Ah, that sounds good. Yeah.
Yes.
So it's a two-choice scheme where one of the choices is +1.
Right. Right. Yeah, exactly. It's a two-choice scheme where it's where you have dependencies between the two choices, and it's actually being used. You put it in two of the I+1, I+2. And then if you do it in this case, then if a server falls, then you can reconstruct everything, locally from the bins next to it. That's basically the main advantage. But it's very, very hard. It's a very hard scheme to analyze. And, all right. So I'm sorry for being 6 minutes over time, and thank you.
Can we skip any questions? further questions, I mean, nobody's going